So it's a pleasure to welcome back Praneeth from Microsoft Bangalore, and he'll talk about how to escape saddle points efficiently.
Hi. So originally I was planning to speak on a different topic, but after spending the few days here, it seemed to me that this may be a more appropriate thing to talk about. So I'll be talking about how to escape saddle points efficiently. This is joint work with Chijin, who is now at Princeton, Mike Jordan, Rong Gay at Duke, and Shyam Kakade from the University of Washington. Okay. So the setting of this problem is non-convex optimization, where we wish to minimize a function f in terms of a variable x. So I'm constrained, and probably don't have to speak about the various applications that this general framework has. And one of the most basic algorithms that people use in solving these non-convex optimization problems is gradient descent. And so the update is given xt plus 1 is xt minus step size eta times gradient of f at xt. And the first question that we would ask ourselves is, how does gradient descent perform, right? And for non-convex functions, it turns out that the answer is that it converges to first order stationary points. So first order stationary points are those where the gradient is equal to 0, and more quantitatively, if we define epsilon first order stationary points to be those where the norm of the gradient is less than or equal to epsilon, it's very well known that gradient descent finds epsilon first order stationary points in about 1 over epsilon square iterations. Okay. Okay. So in general, how do first order stationary points look like? They could be of 3 different varieties. They could be either local minima, local maxima, or saddle points. And whether a point belongs to either of these 3 categories can be usually inferred by looking at the Hessian at that point. So if the Hessian at a point is positive semi-definite, meaning that all the eigenvalues of the Hessian are greater than or equal to 0, then it's usually a local minimum. And if the Hessian is negative semi-definite, it's usually a local maximum. And if the Hessian is indefinite, meaning that it has both positive and negative eigenvalues, then it's a saddle point. And points which satisfy this Hessian PSD property are also known as second order stationary points. Okay. First order stationary points are those where the gradient is equal to 0, and second order stationary points are those where the Hessian is positive semi-definite in addition to the gradient being equal to 0. Yeah.
Just for the Folklore thing you mentioned in the
yeah.
slide, it's a good occasion for me to understand this Folklore, because I discussed exactly the same thing.
Yeah.
You said 1 over epsilon square iterations to get to an epsilon
you will have encountered at least epsilon critical point. Maybe you'll not be there, but in the course of like t iterations, you would have visited it at least once.
So this is independent of dimension?
This is independent of dimension.
And this is proven?
So the only assumption that I make about the function here is that the function is smooth, meaning that the Hessian is bounded above and below. Bounded, yeah. And I think the main difference from your setting is because you have Langevin, where even if you
no, we did it also with gradient flow, and we don't get close to anything.
I mean, the main reason, I mean, maybe when I go to the appropriate place, we will actually see a proof of this. And the main idea is whenever the function is smooth, meaning the Hessian, norm of the Hessian is bounded, then you can choose a step size so that you always decrease the function value. Okay. And and the function is actually lower bounded as well. So in your case, like if the maximum to the minimum is like exponentially large, this will not be true. So the OE also, so the things that the O hides are the starting point minus the minimum value and the norm of the Hessian. These are the 2 things that are hidden in the O notation.
Now it's compatible. It's not an exponential, but it's, I get it.
Okay.
It's okay.
Okay.
It's kosher.
Okay. 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 So we saw that first order stationary points are the points that gradient descent finds, and they could be either like one of these 3 things. Okay. And the question is, in applications that we are actually interested in using gradient descent in, when we find a first order stationary point, does it look like this or this or this? So that's of interest. And people have studied this question in several settings, including neural networks, matrix sensing, matrix completion, robust PCA, tensor factorization, and a bunch of problems where people have tried to look at how many first order stationary points are there, and do they look like these or these or these, and what fraction of them look like this, and so on. Yeah?
So in your setting, the function may be nonconvex?
Yeah.
And
Yeah, I use a fixed learning rate. Yeah.
So this will be defined by the Cauchy, by the Lipschitz constant, right?
By the smoothness parameter, which is like the norm of the Hessian. Like I assume that the Hessian is bounded uniformly. Yeah. So the Hessian is bounded uniformly in the entire space, and then my learning rate depends on the norm of the Hessian, this uniform bound on the Hessian. Yeah.
Just go to the previous thing. Suppose we are at a saddle point.
Yeah.
And we go to a eigenvector direction. We find a eigenvector direction where this lambda mean is negative.
Yeah.
So one of the
Yeah.
eigenvalues is negative.
Yeah.
So then we can escape that.
Yeah. So I'll come to it.
So what is it difficult to find those kind of eigenvectors?
Yes. Because you have n directions, and it's hard to find if you have only a few. When you're high enough, you have plenty of those directions, but otherwise it's hard. Especially if it is small in magnitude, then you know it's very
Yeah.
large magnitude.
Yeah. So I'll maybe quantify these aspects as I go along. But for now, I mean, let's not jump the gun. And yeah, I'll come to your point whenever.
But you know, this meeting has been called a discussion meeting.
Yeah.
Last afternoon started.
You guys that you should stop. This is my point.
Sure, please feel free to ask questions. Okay, so right, so people have studied how do first order stationary points look like in all of these different problems, and the two main observations that people have made from all of these studies is that there are an exponential number of these first order stationary points, and in fact most of them are actually saddle points, meaning most of them actually have negative eigendirections. Okay. And gradient descent, if you start somewhere close by, or if you start particularly like at the saddle point, you can actually get stuck near them. And on the other hand, the good news turns out to be that if you look at second order stationary points, which are points where both the gradient is equal to 0 and there are no negative eigenvalues in the Hessian, then it turns out that they are not just local minima, but they are almost as good as global minima. And the main conclusion that we can draw from this is that finding first order stationary points is not good enough, but if we are able to find second order stationary points, then it's indeed sufficient.
So why would that be true?
So
It's not true, for instance.
it's not true for general. That's why I'm giving like very specific examples.
Even on those examples, that's not true.
Many of these, I mean,
So
these
for instance, in tensor PCA, that's not true.
in tensor PCA is not true, but that's why I'm giving like there are at least some concrete and specific examples where this is true. For example,
I don't know. I don't want to.
yeah.
It's hard to see this. It's you need a lot of. In general model, it's very difficult to see that. So
In a general model, it's definitely not true.
When you want to fix the index, computation becomes very hard. So you can do it only in nice models. So I don't know how they prove that. It's true in the p-spin model, for instance, that the point with diverging index it was index non-zero dominate. It's true, and it's true that the local minima are low, but they are not. They are a fraction above the global minimum. They are way above the global minimum. So, and it's the same thing in tensor PCA. You have local minima in tensor PCA, which are around the equator, which are way above.
Yeah, yeah, yeah.
So
I guess like the examples that you are talking.
It's the same thing for the hard ones.
So that's why I'm not particularly talking about maybe the hard examples. So these definitely do not fall into the hard settings that you are describing about.
But I'm saying that, are you sure these are mathematical proofs?
Yeah, these are all mathematical proofs. Yeah. I mean, one example is phase retrieval, for example. So phase retrieval is one of the things that you also mentioned. So in that.
Phase retrieval belongs to the category I call K equal to.
Okay. Yeah. So actually, like almost all of these belong to that category. K equal to 2. K equal to 2. Yeah.
I'm happy.
Yeah. Because I mean, most of these are actually matrix factorization related problems. So they do belong to the K equal to 2 kind of case. Okay. Yeah. Meaning that you can bound the suboptimality of these second order stationary points. Yeah. So because of these two observations, we then would like to find second order stationary points, right? And then we ask whether gradient descent can actually find second order stationary points. And it turns out that gradient flow, if you go to the setting of like infinitely small step sizes when you are actually doing the flow algorithm, it's known that even with random initialization, with probability 1, you will only converge to second order stationary points. But this is not really quantitative, meaning that you could spend an exponential amount of time close to saddle points before you eventually escape and converge to second order stationary points. Whereas in this work, we are interested in understanding what are the quantitative rates of escaping saddle points and then converging to second order stationary points. And there was a previous work by Ronge and others, which basically says that so gradient descent by itself cannot really do anything, right? Because if you indeed start at a saddle point, you just stay there. So you need to add some amount of randomness, and the randomness that this paper considers, for example, is every iteration of gradient descent, you add some amount of perturbation. So you do gradient descent, you perturb it a little bit, and then you again do gradient descent and so on, right? So when you do this kind of algorithm, they show that perturbed gradient descent converges only to second order stationary points, and in fact it finds an epsilon second order stationary point. I'll define this like epsilon now quantifies both the gradient and the smallest negative eigenvalue of the Hessian. Okay, so it finds an epsilon second order stationary point in poly of d over epsilon iterations, where d is the dimension of the underlying problem and epsilon is this parameter. Okay, so perturbed gradient descent can indeed find these second order stationary points in poly of d over epsilon iterations. And one thing slightly curious about this is that even though gradient descent is a first order method, it never looks at the Hessians, right? But we are able to say something about the converging Hessian of the converging points. So it's slightly curious in that sense, but this is indeed true. Okay, so the first question we now ask is especially inspired by the fact that the dimension of the problems that we are usually interested in is pretty high. We want to ask whether we can this dimension dependency is actually necessary, or we can actually say that perturbed gradient descent can converge to second order stationary points in a number of iterations which is essentially independent of d. So as we saw, the number of iterations for finding first order stationary points was only 1 over epsilon square. It had no dependence on the dimension, whereas here we have a polynomial dependence on dimension, and we would like to understand whether this is real, or we can actually ensure that perturbed gradient descent converges to second order stationary points in pretty much independent of the dimension. Okay.
So what is perturbed?
Yeah, so I'll come to the algorithm, but at a high level, what it does is you take a gradient step and you add a small amount of random noise, and then you again take a gradient
So
step.
it's like Langevin, but with discrete steps.
With discrete steps, and also the limit, the amount of noise you add is in a different scale. Yeah. Yeah. When you take the limit, it will probably approach gradient flow rather than the Brownian set. Yeah. Yeah. Yeah, so here I am adding this perturbation explicitly. I am adding the perturbation on top of like exact gradients, and you could ask, in practice people do stochastic gradient descent, which can be thought of as gradient descent plus some additional perturbation. In our work, we will assume like very specific kind of perturbation that we do, and you can actually relax it to some other kind of things. But in general, unless you have some assumptions about the kind of noise induced by the stochastic gradients, you cannot really say much. Okay, so the first question we would like to ask is whether perturbed gradient descent converges to second order stationary points efficiently, meaning can we remove this polynomial dependence on dimension? And this we can answer almost affirmatively, in the sense that the polynomial dependence on dimension can indeed be reduced to a polylogarithmic dependence on the dimension, and the poly of 1 over epsilon can be tightened to 1 over epsilon square. Okay, so this is basically the same as what we had for the convergence of first order stationary points, except for this overhead of polylog d. Okay. Now, if we go back to the convex setting, yeah.
So for this, do you have assumptions like the model is simple, or?
This has no assumption. I mean, again, the O actually hides constants which depend on the initial suboptimality of the function and then the maximum norm of the Hessian. These are the only two things that are being hidden by this O notation. But apart from this, I don't have any assumption. Okay. So in the convex setting, we saw that gradient descent is indeed not the optimal algorithm, and we also discussed accelerated gradient descent algorithm, which is indeed an optimal algorithm for the class of smooth convex functions. And in practice, it turns out that even though results on accelerated gradient descent were proved only for convex functions, in practice, after an influential paper by Sutskever et al., where they observed empirically that accelerated gradient descent is much faster than gradient descent for neural network training, people have been using accelerated Nesterov method, accelerated gradient descent or gradient descent with momentum quite extensively even in the optimization of neural networks. And in the best result that we know of prior to this work in theory is that accelerated gradient descent can find again only an epsilon first order stationary point in the same iterations, 1 over epsilon square iterations, and this would then suggest that there is actually no improvement over gradient descent. Okay. And in this work, what we ask is whether whether accelerated gradient descent can actually find second order stationary points and not just first order stationary points along with like perturbation, and that too faster than gradient descent. And for this, we can actually show that accelerated gradient descent can find second order stationary points in polylog d over epsilon to the 1.75 steps compared to the polylog d over epsilon square that gradient descent has. Okay. And there are two, so the reason I say essentially AGD is because we do have to do some modifications. So the first modification is that of perturbation, because without perturbation we cannot really escape the first order stationary points. And the second modification, which at this point we have to do because of proof issues and we don't know whether it's really required or not, is something called negative curvature exploitation. And I'll explain what exactly this is when I come to the appropriate part in the proof. Yeah.
So the 1 over epsilon square for gradient descent is with this added noise for reaching second order stationary.
Yeah, yeah.
So that's same as SGD, not SGD, but
gradient descent. Yeah, gradient descent can only find first order stationary points.
The previous slide really said that momentum does not help, or Nesterov's momentum.
That's the best result known, I'm saying.
You add noise.
No, I'm saying this is the best result known for non-convex optimization for Nesterov's AGD, and I'm saying you can actually improve that under some third order smoothness assumptions. I'll talk about that to 1 over epsilon to the 1.75. Sorry? Yeah. So noise is required to escape first order stationary saddle points, first order stationary points. And on top of that, we do some more modification, which at the moment we require for proof purposes, but perturbation is required to escape first order stationary points. Okay. Okay. And so I would also like to mention that this rate, so we are not the first to get this improved rate. And there are previous papers, one by Karman et al. And the other one by Agarwal and others, which show that you can indeed achieve this improved rate, but the algorithm that they propose is more complicated version in the sense that they're solving a sequence of regularized problems. And once you do some regularization, you can kind of do the convex analysis, and so they can solve a sequence of regularized problems where the regularization constant keeps going down and so on. Okay. Of f of x, yeah. And then you use accelerated gradient descent on this regularized version, and then after some point you again decrease regularization. I mean, they give specific ways of how to decrease regularization and so on.
What is the regularization?
It's just L2 square between some iteration. So you have phases, and in each phase you regularize with respect to the starting point with L2 square. Yeah, and then you run this phase, and at the end of the phase, then you again decrease the regularization constant, and you again regularize with respect to the older point. Okay. 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 So let me summarize all the results that I mentioned, and then I'll go on to the proofs of these results. So we saw that convergence to second order stationary points is indeed important in several applications that I described, and so here is the definition of epsilon second order stationary point. So the norm of the gradient is less than or equal to epsilon, and the smallest eigenvalue is greater than or equal to minus square root epsilon. Okay. And for perturbed gradient descent, we can show that they converge to epsilon, they find epsilon second order stationary points in poly log d or epsilon square iterations. And for accelerated gradient descent, perturbed accelerated gradient descent with a new component called negative curvature exploitation, we can show that it finds epsilon second order stationary points in poly log d divided by epsilon to the 1.75 iteration. So this is an improvement from epsilon square. Okay. So the results are clear. Any questions here? Okay.
So
yeah.
these second order things, you assume that the minimum eigenvalue is essentially non-negative, almost.
Yeah, yeah.
But you don't say anything else about the other eigenvalue. So it could be there that you have only one direction that goes.
Yeah, it could only be one direction or more. Yeah. We don't make a distinction between them.
And this doesn't play a role.
This does not play a role. I mean, even if you only have one negative eigenvalue, that's where this actually log d comes in, because it's 1 out of d. And the main point is, even if you only have one negative eigenvalue which is smaller than minus square root epsilon, you only take like poly log d steps to actually escape in that direction. So this may be, yeah, kind of answers. Yeah.
If you take epsilon 1 and epsilon 2
Yeah.
instead of the same,
Yeah. So yeah, you can get a bound and.
so what is the dominant error? You don't have the same power, right? For epsilon 1 and epsilon 2.
Yeah.
The first one and the second one is not
Yeah.
the same.
So epsilon 1 and epsilon 2, you can actually write the complexity separately in epsilon 1 and epsilon 2, and it turns out that like this is the scaling which makes both the terms equal. So that's why this scaling is used by people. So in particular, like you'll get something like 1. So if this was epsilon 1 and this was epsilon 2, you'll get something like 1 over epsilon 1 square plus 1 over epsilon 2 to the 4. So yeah, that's why we choose epsilon 2. Yeah. Okay. So I guess single loop just means that you are running one algorithm as is, meaning gradient descent, I would call it a single loop because you're just doing iterations and so on, right? Whereas what this does is you have say 2 loops. In the outer loop, so there are multiple epochs, and so this is basically the 2 loop structure. And from a theory point of view, I guess like it's not super important, but in practice it's important when you're trying to implement the algorithm, because you want to somehow vary different parameters of the algorithm, and having a single loop makes it much easier to vary the parameters within, as opposed to like having multiple loops where there are many more degrees of freedom that you have to explore to see what's the best thing you can do.
Yeah. I'm completely lost with this result. Something is strange, but it seems like I know if multiply this f by a very large constant.
Yeah.
It's the same problem.
Yeah. So, but that's why, yeah, that's why I'm saying this O hides the initial suboptimality, right? So f of x0 minus f of x star, if there is a global minimum. If you multiply the whole function by a constant, so the numerator goes up, and also like the gradients and these things also go up. So those things cancel in the numerator and denominator. So it will be scale invariant.
So the constant is different. The scale of the function is in the numerator.
Is in the numerator. There is a parameter. There is something here which has a scale of the function. So just changing epsilon will not automatically improve or decrease this, because like both of them cancel. Okay, so let me give you the main ideas of the proof of gradient descent, and so these are the only 3 assumptions that I'm going to make about the function, and right. I guess like it will still maybe not make it clear with respect to the point that you mentioned, but so you should believe me that there is a term in the numerator which captures the scale of the function, so that when you scale the whole thing, the bounds that I get here are invariant. They don't change at all. Yeah. Okay. Okay. So the only assumptions that I'll be making about the function are these 3 assumptions. The first one, and I mean only the first 2 assumptions are really important, and I'll talk about the third assumption. So the first assumption is that the function is gradient Lipschitz, meaning the norms of the gradients change by at most some constant times the norm of x minus y. Okay, this is what we call the smoothness assumption. This also is equivalent to saying that the Hessian has a bounded norm. The second assumption is the Hessian-Lipschitz assumption, meaning that the operator norm of the difference of Hessians between two different points x and y is some constant times norm of x minus y. Okay. So this is like the third order smoothness condition. So this is second order smoothness. So we are bounding the second derivative here, and this is kind of bounding the third derivative. Okay. And the bounds that I'll describe will depend on the constant here and the constant here, but I'll not make it precise in the talk. Okay. So there is a constant here and there is a constant here, and the bounds that I'll get will depend on these constants. So the third assumption, which is more for the sake of simplicity, is that the function is lower bounded, meaning that it does not go to minus infinity. So in the absence, so if we have this assumption, we can show that our algorithm will find an epsilon second order stationary point. If we don't have this assumption, what we'll be able to say is that either the function finds a second order stationary point, or it would have decreased the function value by a lot. And this assumption basically tells us that because we cannot decrease it by a lot because the function is lower bounded, you have to have found a second order stationary point. Okay, that's the only role played by this lower boundedness assumption. So the main two assumptions are the gradient Lipschitz and Hessian Lipschitz assumptions. Okay. Okay, so let's try to understand how gradient descent behaves. So the gradient descent step is this xt plus 1 is xt minus theta grad f of xt, and there are actually two situations. So one when the norm of the gradient is large, and the other one when the norm of the gradient is small. When the norm of the gradient is large, we can actually use the gradient Lipschitz assumption and argue that the function value strictly decreases by a value which depends on the norm of the square norm of the gradient. Okay. So we have f of xt plus 1, and xt plus 1 is xt minus theta grad f of xt, and if we know that the second derivative, the Hessian, is bounded, then we can, and we choose the step size to be less than 1 over the spectral norm of the Hessian, then we can indeed show that the function value at xt plus 1 is less than or equal to f of xt minus the step size over 2 times the square norm of the gradient. Okay. So if the norm of the gradient is large, then we actually have a large decrease, and because the function is lower bounded, we cannot have too many of these steps, right? And that's basically the argument in saying that we will find a point. So we'll eventually have a lot of points where the square norm of the gradient is small. Otherwise, we just keep decreasing the function, and the function can only decrease so much. Yeah. So this is also the argument for the 1 over epsilon square convergence rate for first order stationary points. Okay. Okay. So now let's consider the setting where the norm of the gradient is small, and there are two possibilities. One, it could be a second order stationary point if all the eigenvalues of the Hessian are like almost positive, or it could be a saddle point if there is a pretty large negative eigenvalue of the Hessian, right? But unfortunately, because we only are looking at the gradients, we cannot really tell whether we are in this situation or this situation, right? And so the main question is to understand whether we are in this situation or this situation, and if we are in this situation, how do we escape, right? So that's the question of escaping saddle points, and the algorithm that we use to actually escape these saddle points is this perturbed gradient descent, where we run this iteration, and every time we check whether the perturbation condition holds. And if a perturbation, I'll explain what the perturbation condition is. If this condition holds, then I'll perturb xt to be xt plus the zeta t, where zeta t is drawn uniformly from a ball of radius epsilon around 0. So we are at xt, and we just slightly perturb in a ball of radius epsilon. And if the perturbation does not, and in any case, we then run a gradient descent step. Okay. Because we don't have access to the Hessian. We only have gradient, and we don't know if the Hessian has a negative eigenvalue or not. Yeah. Right. So the algorithm is very simple. So you just do gradient descent, and whenever a perturbation condition holds, in addition, you do the perturbation. Okay. So between two perturbations, we are just running gradient descent, right? And the perturbation condition that we have here is the following. We check whether the gradient at xt is small, and we also check whether we have not added any perturbation in the last several iterations. Okay. So if both of these are satisfied, then we add this perturbation. Otherwise, we don't add the perturbation and just run gradient descent. So we see that we are adding the perturbation only when the gradient is small, and between any two perturbations there is at least some amount of gap, because we are checking that we have not added any perturbation in the last several iterations, only then we add a perturbation. So it means that there is a minimum gap between the time we add any two perturbations. Okay, so this will be useful when we go forward. Okay. Okay. So how does something like this actually help in escaping saddle point? So let's try to look at this animation. So when we are at the saddle point, we gave a perturbation. So the point moved, this red point moved from here to here, and then from this point we'll just do gradient descent, because we are not going to add any perturbation for several more iterations, right? When we do gradient descent from here, so it gradually finds this negative direction and eventually escapes. Now this may still be somewhat misleading, because this is just some two-dimensional structure and the initial perturbation already had some constant component in the negative direction. Whereas when we are in high dimensional space and we are doing a random perturbation, in general we will only have 1 over square root d fraction of the perturbation in the, if you only have one negative eigen direction, we only have 1 over square root d component in the negative eigen direction. And the main part of the proof then would be to show that this 1 over square root d actually affects us only logarithmically, and that will be the main part of the proof. Okay.
So you're saying even if it's hard to find the only direction,
yeah,
this little bit is
little bit will give you like 1 over square root d, and that's already enough. And the main intuition for this is the power method for finding the top eigenvector, where even if you start with a random vector, if you have say a symmetric matrix, you keep let's say positive symmetric matrix, you keep hitting a random vector with that, and within log d iterations you will converge pretty close to the top eigenvector, and that dependence is only logarithmic, and that's basically the intuition that will appear here. Okay, yeah.
At every step, because you want to preserve the rate of gradient descent later.
Actually, we have another paper where we can show that even if you add perturbation in every step, it's fine. But the proof of this is much simpler than adding perturbation at every step.
Oh, this is simpler.
This is simpler, yeah. I mean, the main reason this is simpler is because between two perturbations, you are just doing gradient descent. And so maybe when I go through the proof, it will be clear why this intuition helps in the proof.
So here, how do you know that the curvature is strong enough?
Yeah, so that's why.
A little bit, and this curvature is kind of.
Yeah. So that's why. So in the definition of so second order stationary points, we have this square root epsilon, right?
So you put all these in the.
So that appears in this, like number of iterations, depends polynomially on this, but only logarithmic.
Point is those who don't satisfy that.
Yeah. So it could still be a saddle point in like exact terms, but in quantitative terms, it's
you discount.
yeah. Sorry. The magnitude of the negative eigenvalue is like minus square root epsilon or more. Yeah. Okay, so how do we go about this? So in order to understand like the convergence rate of what gradient descent, perturbed gradient descent does in this setting, so let's consider the set S of points. So let's consider a saddle point, and let's consider the set S of saddle point, set S of points around the saddle points in the unit ball, from where gradient descent does not escape quickly. Okay, so let me maybe try to. So let's say this is a saddle point, and this is a ball around the saddle points, and let's say S is a set where this is a bad set. So if I do gradient descent from any of the points here, it stays there for very long, okay? And because when I'm here, I'm going to randomly perturb in the entire unit sphere, the probability that I'll fall in this ball depends on the volume of this set, right? If I can show that the volume of this bad set is small, then when I do the perturbation, with high probability I'll fall outside of this bad set, and then from there, because I'm just doing gradient descent, I'll escape very quickly. So the main technical point would be to compute the volume of this bad set S, right? And that's what I'm saying here. And also, like technically the definition that we use for escape is that the function value decreases significantly. Okay.
This is no reason to be small. If you have just one direction,
yeah,
the function minus x minus constant x1 square.
Yeah.
And that's it. zero everywhere. The bad set, so you are exactly on a sphere, you have the equator and the...
Yeah. So when I say it does not escape quickly, so from any point other than the saddle point, the gradient descent will definitely escape, right? It just depends on how long does it take to escape, right? And when I mention quickly, I have a particular term for what I mean by quickly. And when I set this to be of the order of log d divided by something that depends on the negative eigenvalue, the volume of this set indeed does become small. So maybe let me go through like the one dimension. So okay. So if at least the idea is clear, even if you don't believe me, so if the idea is clear that I want to show that the volume of S is small, we'll try to give intuition for why this volume will be small. Okay. Okay. So let's just consider the two-dimensional quadratic case where the function f is x transpose 1 0 0 minus 1 x, right? This has one positive eigenvalue and one negative eigenvalue, and at x equal to 0, the gradient is equal to 0, right? So 0 0 is indeed a saddle point. Okay. So when you do gradient descent starting at 0, you can write an explicit equation for the gradient descent updates, and that's xt plus 1 is this matrix times xt with 1 minus theta and 1 plus theta on the diagonals, right? When I keep doing gradient descent multiple times, I'm just hitting this matrix multiple times to xt, right? And the points okay, so as I keep multiplying this, the first coordinate will become close to 0 because this will be raised to 1 minus theta to the t, whereas the second coordinate will be raised to 1 plus theta to the t, right? The second coordinate will grow large, and as second coordinate grows large, we are actually decreasing the function value. So in some sense, we are actually escaping away from the origin whenever the when the second coordinate is basically 1 plus theta to the t times x 0 2 in the second coordinate, right? And as long as the second coordinate of the starting point is not too small, I'm going to increase it exponentially fast because I have this 1 plus theta to the t. Okay. And so here I have this so I'm assuming that the negative eigenvalue is minus 1, which is like a constant, but if this were not constant but minus square root epsilon, this would be 1 plus eta square root epsilon, and that's where you would get a dependence on the epsilon, but the dependence on the dimension itself will be only logarithmic because as we'll see. So in this case, for example, the bad set S is actually a thin strip because for it not to escape, the second coordinate of x 0 should be very small, and that's like the strip around the origin, and because of this the volume of S is small. Yeah.
So maybe you sort of answered it, but so if the size of S is large, the volume of S is large, you can't take a really big theta just over there. Like only when your perturbation condition goes, then just take a large, then you won't be sort of escape even if you have a large size. Even if the volume of S is
I don't know if step size alone can help you because you somehow have to eventually figure out the direction. So direction is indeed important. Yeah. Okay. So let's go to the three-dimensional example. In the three-dimensional case, so let's say there are two eigenvalues which are equal to 1 and one eigenvalue which is minus 1. So this is again a quadratic. 0 is again a saddle point, and the gradient descent update is again a linear update equation with two eigenvalues 1 minus theta to be less than 1, and one eigenvalue which is greater than 1 plus theta. And the only way that xt does not move away from 0 is that the third coordinate of x0 is very, very small. That again corresponds to a thin disk around the origin, and because this disk is thin, the volume of S is again small. And this also kind of gives you the intuition for why the dimension only appears logarithmically, because if I had d minus 1 of these and only one of these, even then so x0 this will be, so if I take this width to be 1 over square root d, then the volume of this is going to be very small, right? And for 1 over square root d to be overcome by this 1 plus theta to the t, you would need t to be 1 over eta log d, right? So that's the reason why you only have logarithmic dependence on the dimension. Yeah. Okay. So both of these were for quadratic cases, and the key technical result is that even in the general case with only like the Lipschitz assumptions that we had, the set S is like a thin deformed disk. This is not a very precise term, but I'll tell you what exactly I mean by this. And this would then imply that the volume of S is actually small. Okay. So there are two key ingredients in the proof. The first one is what we call improve or localize, and the second one is a coupling argument. So let me go over both of them. So we saw that by just the smoothness assumption, we can show that f of xt plus 1 is less than or equal to f of xt minus this squared norm of the gradient, right? Now, because of the gradient descent update, we can also write this in terms of the difference between xt and xt plus 1, right? So if we rearrange this, what we see is that xt minus xt plus 1 square is less than or equal to 2 eta times the function value decrease. And this actually tells us something quite interesting, because what it says is that if either you may decrease the function value significantly, or if this is actually small, then it means that you actually have not moved much, right? So that's why we call this improve or localize. So either you improve the function value difference, or you localize, meaning that xt plus 1 is not far away from xt. So when you add all of these up and then you apply Cauchy-Schwarz, what you can say is that x0 minus xt square, the distance that the iterates have moved, is upper bounded by step size times t, number of iterations, times the amount of function value decrease, right? So at high level, again, either you have decreased the function value, so either the function value decreases significantly or the iterates do not move much, and this is why we call this either you improve or you localize the behavior of the points. So the second part of the argument is this coupling argument. What the coupling argument does is, let's say you fix 2 points u and w, and u and w differ exactly in the negative eigendirection by like a 1 over square root d distance, right? Then what we can argue is that either gradient descent from u escapes or gradient descent from w escapes. And in particular, this means that both u and w cannot simultaneously fall in the bad set S, right? And this basically says that if you look at any ray which is parallel to the any line which is parallel to the negative eigendirection, then the width of this bad set S is at most 1 over square root d, and this is enough to tell us that the volume of this bad set is small. Okay, so let me try to expand on how we can say this. So the main idea is this: so if gradient descent from either u or w goes outside this ball here, then using improve or localize, it means that we should have decreased the function value. On the other hand, if gradient descent from both u and w lie in the same small ball, we can use local quadratic approximation because of the third because of the Lipschitz bound on the function. And for quadratics, we explicitly saw that the bad set S has very small volume, right? And so we can use that to show the claim for an exact quadratic, and we can bound the approximation error between the function here within this ball and the quadratic within this ball using the Hessian-Lipschitz property, and that's the main idea of this proof. Okay. So just putting everything together, so we have this gradient descent step where xt plus 1 is xt minus theta grad f of xt. If the gradient is large, then the function value decreases. If the gradient is small, then we are either at a saddle point or at a second order stationary point. If we are here, we are fine, but we are not sure whether we are here or not. So we just add perturbation in both the situations and then just run gradient descent. If you are at a saddle point, we would have decreased the function value, so this is fine. And if you are at a second order stationary point and then we do this, either we move away from the second order stationary point, in which case we can use improve or localize to say that the function value indeed decreases. Otherwise, we just stay there and we are still fine because we are at a second order stationary point. So this basically is a overview of how we argue the convergence rate of perturbed gradient descent for finding second order stationary points. Okay. So let me now briefly talk about the main ideas in the proof of accelerated gradient descent. So the algorithm is given here, and this is actually written differently from what I presented in the convex optimization lectures, and this actually is much closer to the physics intuition. So we have, so in Nesterov's accelerated gradient descent algorithm, we have two things that we keep track of. One is iterate xt, and the other one we call velocity vt. Okay, and again, like we should think of this as the location of like the particle, and this as the velocity at that particular point of time. So the next xt plus 1, the next position of the particle is going to be given by xt plus 1 minus theta vt. So it's going to move from xt in the direction of the velocity for a little bit, and then it's going to take a gradient descent step at that point. Okay, so we are at xt, we move slightly in the direction of the velocity, and then we take a gradient descent from this new point. So that's xt plus 1, and the velocity, new velocity vt plus 1 is just xt plus 1 minus xt. Okay. Okay, so the main challenge in understanding the behavior of accelerated gradient descent for non-convex functions is that all known analysis of accelerated gradient descent has been for convex functions, and the potential functions that they use to keep track of the behavior of the algorithm do depend on the optimum x star. For convex functions, the optimum is well defined because there is a single or they're all connected, but for a general non-convex functions, there is no notion of x star. It's not even clear where we are converging to. So we cannot use anything of this sort in the argument. So the main challenge was to develop what is a potential function that can help us understand the behavior of this algorithm in the non-convex setting. And in hindsight, it actually seems kind of quite trivial what the actual potential function that we should be looking at is, because accelerated gradient descent is indeed a discretization of this ODE, where, so if we ignore this second term, right, if it was just x double dot plus grad f of x equal to 0, this is just the equation of force equal to mass times acceleration, right, where x double dot is the acceleration and minus grad f of x is the force field, because f is the potential function, minus grad f is the force field, right, and this theta twiddle x dot corresponds to adding a friction term. So the friction, theta twiddle is the friction coefficient and x dot is the velocity. So this is indeed giving the Newton's law of motion for a particle in a potential field f and in the presence of friction with a coefficient theta twiddle. Once we have, once we see that this is the equation that we are actually discretizing, we can write down the potential function that we will use for this one, which is just the potential energy plus the kinetic energy, right? F of x t2 is the potential energy at time t2, and x dot t2 square, so mass is equal to 1. So velocity square is the kinetic energy at time t2. So the total energy at time t2 is equal to total energy at time t1 minus whatever has been dissipated in friction, right? So the Hamiltonian f of xt plus half x dot t square decreases monotonically, and it turns out that, so this was for the continuous ordinary differential equation, and it turns out that the same thing is true even when we discretize it in the way that we have done here, iterate being xt and velocity is xt minus 1. The Hamiltonian indeed decreases monotonically as long as the function f is not too non-convex, and when I say it's not too non-convex between xt and 2 points xt and xt plus vt, it means that when I look at this one-dimensional function on this line between xt and xt plus vt, I'm measuring non-convexity of this one-dimensional function between these two specific points, okay? And as long as the function is not too non-convex between xt and xt plus vt, we can actually show that this Hamiltonian indeed again decreases monotonically with the algorithm. And in case the function is too non-convex, and then this does not apply, we can actually do something much simpler, which is just reset velocity to be equal to 0, because it seems like we could be moving in the wrong direction, like we might be moving up a hill, and we just reset velocity, or we move in the non-convex direction. So this is what we call negative curvature exploitation. So maybe when we come to this part, I'll explain it a little more. Okay, so I think, yeah.
Continuous equation is always monotonic.
Yeah, yeah.
For this discretization, you're saying it needs this extra condition.
Yeah, it needs the condition on f to be not too non-convex, and then it will decrease. If it is too non-convex, it need not decrease.
If it's too non-convex, then you put in some.
Yeah, we do something else, because this does not, like this discretization and this update is maybe not good. At least we don't know how to analyze it. So we take a different step. So in particular, as I'm saying here, we'll set Vt equal to 0. If you see that it's too non-convex, we set Vt equal to 0, in which case like this automatically decreases, right? And or we move in the non-convex. So I'll maybe explain it in this slide. Okay. So if it's not too non-convex, we just take the accelerated gradient step that I described, the discretization, and we know that the total energy decreases. If it is too non-convex, there are two situations. So one when the velocity is large and the other one when the velocity is small. If the velocity is large, we just said Vd plus 1 equal to 0. This naturally decreases, right? Because this is a positive term and it was indeed large, and then I am just setting it to 0. So Hamiltonian just decreases, right? And in case the norm of Vt is small, we can actually move in either the plus or minus Vt direction, and the intuition for that is the following. So let's say we are xt here and xt plus Vt. We know that it's too non-convex between xt and xt plus Vt, so it has some negative curvature like this. So Vt is in this direction and minus Vt is in this direction. Because the function is too non-convex, so the second derivative always makes us decrease the function value. So we just have to look at the negative gradient and then we just move in the negative gradient direction. So we move in the xt minus Vt direction, right?
Sorry, how do you identify whether it is too non-convex or not?
So we can just measure the function value at xt, xt plus Vt, and so yeah, so the way we do it is we know the gradient of f at xt, right? And then so if it were convex, we know that f of xt plus Vt is greater than or equal to like first order, yeah, convexity condition, and you just verify that here and you see how much it differs by, and that will tell you whether it's too non-convex or not too non-convex. And if it's too non-convex, then yeah, these are the two cases that we looked at. Okay. Okay. So.
But then you need to know the convexity constant, right? Otherwise, you will not be able to verify. So
No, by too non-convex, we have some particular quantity that we are fixing. So that's something that we are saying what is too non-convex and what is not too non-convex. Yeah. Okay. So at the high level thing, so in order for us to get Hamiltonian decrease, what we are saying is if it's not too non-convex, we'll just take the accelerated gradient steps, and this will automatically decrease. Otherwise, if the velocity is large, we just set velocity equal to 0, and because we are setting this to 0, this will automatically decrease by a lot. And if the velocity is small, it turns out that we can actually just move in either the plus velocity or the negative velocity direction, and this again decreases. So whatever we do in every step, the Hamiltonian monotonically decreases, and in both of these situations, it turns out that there is enough decrease in a single step. Okay. Whereas in this step, it turns out that we don't necessarily have a lot of decrease in each step. So we need to amortize a lot of different steps and then take an average of how much overall decrease there is, and then we have to take an average to get us the right convergence rate. Okay. So again, even for whenever, so in this case, right, whenever we do the accelerated gradient step, we again have this improve or localized phenomenon where the total energy at time t plus 1 is less than or equal to total energy at time t minus theta over 2 eta times norm of Vt square. And we can, so Vt was just xt minus 1, right? We can again reorganize this to say that the sum of squares of all the distances moved is at most some constant here times the amount of function value decrease. So we can then use again Cauchy-Schwarz to say that if my function value has not decreased much, then I'm always in a small ball around the starting point. Okay. And we can again approximate locally by quadratic and then perform the computations, but the precise computation in this setting turn out to be much more technically involved. So let me finish here. So to summarize, we saw that simple variations to gradient descent and accelerated gradient descent can ensure efficient escape from saddle points, and the main tool that we developed through this in this problem was to develop a fine understanding of the geometric structure around saddle points. And for the accelerated gradient descent in the non-convex setting, we also had to develop the new potential function and ways of the improve or localize lemma, which were helpful in understanding their convergence behavior. And some of these can also be extended to the stochastic setting. Okay. So some of the open questions from our work were, I mean, the first thing that we have not been able to resolve is whether the negative curvature exploitation step that we add is indeed really required, or it's something that we require only for the proof. There are lower bounds for non-convex optimization, and there There are actually even more recent works in 2019 and so on, but there are still gaps between upper and lower bounds for finding second order stationary points in the non-convex optimization setting. And all of these results have not yet been extended to stochastic setting. And in the last several years, there have been several specific and structured non-convex optimization problems where people have developed faster algorithms just directly based on non-convex, local non-convex optimization rather than going through convex relaxation approaches, even though both of them give global guarantees. But the non-convex optimization approaches turn out to be faster than the convex relaxation approaches. And there seems scope for using these algorithms in other more structured problems as well. So,
Can you say a little bit about those?
so these are mostly actually related to, yeah. So these are mostly matrix factorization related problems. So examples include matrix completion.
So who did that?
So we have some results on alternating minimization, and then there are a lot of other people who have also done for gradient descent.
Like who?
Ronge, Tengyuma, and also optimization people.
But these algorithms stay on the first order. They don't use Hessian for it.
They don't use Hessian. Yeah. Yeah. Okay. So I guess that's all I had to say. Thank you.